And this event is sponsored by Python Software Foundation at diamond level. And just a friendly reminder, we have a HackMD for sure note taking, so feel free to join it and contribute. And if you have any question, you can submit your question to Slido. We will answer it later. And now let's give a welcome to our speaker, Utkarsh Goel, like UG. And he is a co-founder and CTO at Clearbot. Today's topic is talk about the Python make robot easy. So let's welcome.
All right, thank you so much for coming in to listen. I'm going to be talking about how Python can make robots easy. A little bit of background about myself. I studied engineering at the University of Hong Kong, graduated in 2020, and then co-founded a company called Clearbot. And at Clearbot, what we do is we build boats like these that clean up waterways around the world. At the moment, we're in Hong Kong, India, and Southeast Asia. We got a Forbes 30 under 30 Asia listing for that as well. So just to give you a little bit of background on what we are going to achieve by the end of this talk, we are going to be building a simulation because I could not get a robot on the flight through customs. But we're going to kind of try and simulate it on screen. And this is something that you could do as well. You don't need to buy expensive hardware to run these kind of simulations. And the idea is that we're going to get a robot to move in a straight line, right? I got somebody to talk to me outside, and he said, hey, I couldn't get a robot to move in a straight line. So I told him, you can attend this talk because I'm going to kind of cover exactly that, right? And all of this setup can actually be reproduced with something as basic as a Raspberry Pi and something called a Pixhawk. It's an open source sort of drone controller hardware that you can just use to reproduce whatever we are going to do in this talk. It's going to be a little fast-paced, but I'm going to try and answer any questions later as well. So please do ask any questions you might have during the talk. All right. We're going to do some warm-up because there's going to be lots of code that you're going to see on the screen, right? But after we do a little bit of warm-up, I'll introduce you to ROS. I'll introduce you to how to use ROS with Python, and then a little bit of a deep dive into Pixhawk, which is how do you deal with real-world hardware, and what are the firmwares that can kind of help you to do that easily. And then we'll combine all of it together at the end. The last one is the most sort of heavy topic, so I'm going to rush through the first few quickly so that we can spend more time at the last part. All right, I think just to warm up, everybody knows how to run Python on command line, right? Just run Python 3. We're going to use that, right? And everybody here knows a little bit of functions, right? We know that you can write functions using the def keyword and then just define a function, right? And then you can also create classes, right? You can declare a class. For example, here I've created a my class, right? And you can create a init constructor so that we can declare variables and stuff inside that class, right? We'll use all of these basic concepts to do ROS later, right? But before we even get into how to do ROS, the question really that you need to answer is why do you need ROS, right? And if you think about how we build robots, there are n number of things that need to work together, right? You need to have cameras, you might have servos, different kind of motors, and they kind of all just need to run in parallel, right? And if you run a Python command by yourself and you want to do multiprocessing because you want to process so many things together, you'll realize that it becomes complex quite quickly. What ROS gives you is sort of this basic infrastructure, this scaffolding per se, where it will give you ways to run different processes separately, completely independent of each other, but they can talk to each other using something called messages and topics, right? So you don't need to write your own interprocessing. You don't need to even use the complex interprocessing or socket networking. ROS just gives you that from the ground up, right? So you don't have to do any of that complex stuff, right? And it has native support for both Python and C++, right? Installing ROS is actually quite easy. We're going to take examples of Ubuntu because installing it on Windows and Mac is fairly complex, to be honest, and is not as reliable as it would be on Ubuntu. And we're using Ubuntu 20. And It's actually as simple as just doing an apt install. There are a few commands that are there on the ROS documentation itself. And documentation for ROS is actually amazing. It just requires a little bit of an introduction, which I hope this talk will kind of give you. After you've installed ROS, here are some of the basic concepts. Now, I'll go a little slower here. So there are 5 basic concepts in ROS that you're going to need to know to understand this talk, right? One is workspace. Now, workspace is like a big folder where everything that you write as your ROS code exists, right? You create a folder anywhere on your home directory, and that's your ROS workspace. It's just a folder, nothing else, right? Then inside the folder itself, you create a src directory, and you write something called packages inside those src directories. Now, these packages are like a unit of code blocks that you can put together. Like, it represents functionality. For example, if I have a robot that needs to read images from a camera and process them and do something, right? I'll have a package called camera processing or image processing, and then I'll create multiple nodes in them. I'll create a node which reads camera images. I'll create a node which processes each frame, right? And now these nodes need to talk to each other, right? So when these nodes need to talk to each other, as I told you, you don't need to create an interprocessing. Instead, you can just send messages. So this image frame that we get from a camera reader can go to an image processing pipeline through just a message, right? So you can interchange these messages, even images, and come what may, right? So that makes your life really, really easy, right? And finally, these messages are exchanged on topics. If you've heard of PubSub before, it follows the same sort of paradigm, where you have a bunch of topics that you can describe in your ROS environment, and then you can exchange messages on that topic of any certain type. So you'll see I have topic 1, topic 2. The topic 1 can be of certain type A, and topic 2 can be of certain type B. And then you can exchange. That means you can publish to those topics or read from those topics from any nodes anywhere on your ROS system, right? So just to revise, we've seen workspaces, packages, nodes, messages, and topics, right? That's all we've learned for now. Now, the next step is, how do you use Python with it? A lot of people actually who want some high performance in ROS would switch to C++, but Python is a great way to get started with it, right? And it makes things really, really easy, right? You just create a package by defining that you want to create a package, and the build type is Python instead of C++, right? And ROS does the basic scaffolding for you again here, where it'll create a folder, it'll create some directories, and you'll see a package 1 folder created in your src directory. And the package 1 directory will have a few things already ready for you, right? It'll have another package 1 folder inside, which stores your source. We'll get to it later. But it also sets it up as a Python package, so you can build it, let's say, with a setup.py file and so on, right? And with a package.xml that ROS uses to maintain its dependencies. What we really care about is this package 1 folder. Inside the package 1 folder, that has our basic source files to get started with. Now, this is a bare minimum Python code that you need to write inside your package 1 folder to get it running as a ROS node. I'll try and go through this slowly. So it's a very basic function, actually that does nothing. It's doing absolutely nothing, but it explains what's the hello world of ROS, right? Which is that you initialize a RCLPy, which is a ROS binding for Python, right? And then you create a node. That means this is the file that's going to define a node, and we're going to just name that node my node. And then we do something called spin the node, right? Now, this spin is a async concept, right? That means that you're basically telling ROS to start running this node and keep running this node until it is terminated. And once it's terminated, you destroy the node and shut it down. So this spin function call is kind of a blocking call, where something keeps running in the background. But as you can see, there's no logic defined here whatsoever, right? And something that ROS already provides us can help us to build. We don't need to know how to build our own Python packages. We can just use something called Qualcomm. It is provided with ROS, and you can just build this package. It's quite straightforward. Documents are amazing. You can kind of have a look. But then once you run the build command, you'll see that there is a build folder, install folder, and a log folder alongside your SRC folders in your workspace. And that's because the workspace itself becomes an installation environment for your code. That means you can isolate your code, run from within this workspace, and make sure that your code runs before you kind of ship it to production, right? We have our Clearbot boards that go out to our clients, to our customers, but they don't necessarily have the source files and whatnot. We have to install it on their computers. But when we develop it ourselves, we develop it on machines where we can inspect into the build folders and so on and so forth. Right, so that's what this workspace helps you do. So before we'd not written any logic. Actually, in this slide, we've still not written any logic. But the left and the right, the before and after you see, is the same code, but written with classes. Now, why we want to write classes is later we're going to have to add logic to our code. And we're going to do that using classes in Python. But just to compare between the two, you can see that we are creating a node instance in the one on the left. And on the right, we've created a class which has a parent class of type node. And then we've created my node as an object instead. And it's doing absolutely the same thing. And that's the idea, that now we can use this class here and start writing things in the constructor that make sense for our business logic, right? And that's exactly what ROS allows us to do. We can start writing code here, right? Now, I hope we remember publishing and subscribing, things that I was talking about in topics, right? So something very simple that you can do in ROS is, in our node, we can create a publisher, and we can say that this publisher messages to the topic, my topic, of type string. Right? Ignore the 10 in front. We kind of will get back to it later. It's something called a QS profile that we don't need to worry about. Right? And then we create a timer, and we say that every second, call this function called timer callback. And this timer callback function is just sending the data hello world to that topic. Right? Now, as you can see, it's very easy to do in ROS. If you wanted to do this in Python by yourself, right, in an environment where you have to set up your own async loops and you have to set up your multi-threading, this can become fairly complex. ROS makes that super easy to do here, right? And then finally, this is more of a Python concept, but to run this from the command line, you need to add a console script so that you can do something called ROS2 run, and then just run that command. But once you set up this basic stuff, right, you put it in your setup.py file, which is what Python uses to build packages, right? You can rebuild your package and then just do a ROS2 run package1 node, and it starts publishing data, as you can see here. And ROS2 allows you to inspect the topics that are there in your ROS environment. You'll see that we have a my topic being shown there, right? Whenever you're publishing to a new topic, it shows up there. Now, there's messages going into that topic. How do you read messages from that topic? You subscribe to them, right? So here in this node, we've created a whole new node, right? And we've called it sub node, right? And all we're going to do is subscribe to data on this topic, right? So we create a subscription this time instead of a publisher, and we give it the same parameters. We say that we are going to receive a string type object from this topic called my topic, right? And whenever we receive the topic, we are going to call back to this function called subcallback. Now, this is great as well, because if any of you have done async awaits, waiting for messages to come in on a channel, let's say in Go or so on, you have to build that out yourself. It's quite easy to do here. You just define a callback, and whenever there's a new message, it just calls that function. And that function has a message type string in its callback definition already. So the message that comes in is just ready for you to use. Again, we follow the same process. We add the sub. You can see at the bottom, we add the sub node as an executable, and then we can start running the subscription. And you see that if this node is publishing, this node starts receiving that data, right? All right. I know that is a lot for somebody who's not been introduced to ROS before, so just quick revision. We've created a package, right? We've created 2 nodes, one subscription node, one publisher node, right? And we've created something called a my topic where we are sending or receiving messages from. And we can have string messages on this topic. We can have any kind of messages on that topic. We'll get into how we define these messages and whatnot. But usually when you're working with, say, images, you're working with some primitive data types, that kind of stuff is already defined for you in ROS. You just have to kind of just import it on the top, right? And finally, we've learned that there's something called callcon, which can quickly help us build the packages and run them, right? All right. I'll just take 2 minutes for a water break. So the next module is the PX4 autopilot or the PixHawk firmware. All right, so this is where in my past experience, I lose a lot of people. So I hope I have your attention because this is pure hardware. And I'll try and go through this as slowly as possible, but I've also tried to simplify it. So one day when you decide to build your own drone or your own rover or whatnot, you know that there's something that exists that can make it easy for you, right? So far we've covered ROS too, right? But now I'm showing you a piece of hardware called PixHawk, which actually cannot run ROS 2, right? But it can run something else. It can run something called a real-time operating system, right? And there is a very big motivation for why we want to do that. Let's take an example of a drone. A drone is calculating a lot of data when it's running, right? It's calculating altitude, GPS locations, accelerometers. It's trying to get feedback from its own motors, from its own sensors in real time, right? And really what RTOS allows us to do is when there's such time-bound tasks, when there's something that's happening super quickly, like you have a new GPS reading and you want to put it into your feedback loop and do something with it, a real-time operating system compared to an operating system is much, much faster and much, much more practical to do, right? You'll see some very basic robots as well, which will, you can control them using a normal Raspberry Pi, but there are limitations to scenarios where you can apply those. And usually when you're using a Raspberry Pi directly to control, say, motors and stuff, you're going to have a middle board which does exactly the same things that a PixHawk is going to do for you, right? So just having a PixHawk there that can do all of that in one single compute is super, super efficient. And you'll again, as a hobbyist, you'll get into a scenario where your drone's not flying stable enough because you don't have a STM chip that can do real-time communications and stuff, right? But the code for the firmware itself is quite complex, right? And what we are going to do is we are going to not touch the PixHawk firmware at all. We're going to try to touch it as little as possible. We're just going to go as far as flashing the firmware, building the firmware, but we're not going to change it. And instead, we are going to use ROS to make life simple for us. So that's why we specifically choose PX4 Autopilot, because it has a great ROS interoperability, which means that you can connect the PixHawk with something like a Raspberry Pi, and you can talk to it with ROS rather than to modify the code yourself and deal with your business cases on the PX4 firmware itself, right? And this is the interface that they provide. It's basically a client and agent kind of a structure where you have a PixHawk, right, which is running your real-time operating system, in our case, a PX4 Autopilot. And then we have a Raspberry Pi, which is running a ROS, our ROS 2 environment, right? And we connect them with a USB UART communication, right? And we delegate the work to different things to do different things. For example, here for PX4 Autopilot, we will be delegating the task of controlling the motors, running the feedback loops for the sensors, and so on, right? And for the Raspberry Pi, we'll delegate the tasks such as connecting to sensors like LiDARs and cameras and whatnot, right? And the second task, very important task, is to talk to the flight controller to put all that data together and make more long-term decisions. Things like how to plan a route from from point A to point B, right? And just give me a minute. Yeah, so, and that's how these two are going to talk to each other and exchange data and all of that stuff that we're going to discuss later. So how do you get started with PX4 Autopilot? There are three very simple steps. You pull the code, you flash the firmware, and you get messages on ROS from the firmware itself, given that you're connected with a USB cable between the two of them. As I said, we're not going to touch the PX4 Autopilot code at all, and that's just because it's really difficult to get started with, especially if you've not done robotics before, right? And you can get the firmware open source. So that's the other great thing, that the whole firmware is completely open source. You can not just read the code, you can also contribute back to it. The community is quite welcoming, quite growing. I've been a part of it for now quite a bit, right? And there has now been times where we've contributed code back from Clearbot to the firmware itself, right? But this is where you can get the code, right? Once you get the code on your computer, you need to set up the toolchain. Now, again, for a lot of people who may have dealt with hardware, you'll realize that toolchains can get really finicky, right? What Pixhawk does, what PX4 Autopilot does really well, is that they give you a single command, and the script already written in the source code of the firmware, where you can just run an installation, right? So all of this on their documentation, very clearly written on how to do that. But once you've set up the toolchain, then building the code is also just a make command, right? So you get the code on your computer, you run a make command, and this is where you have to be careful now. So PX4 Autopilot supports multiple different hardwares, right? Depending on the hardware you get, you're going to have to choose something called a target, right? In our case, we use the Pixhawk 6C, right? So we're going to choose specifically that target, right? So you'll see that when I run the command for, that went by too fast, but when you run the command for your specific target, your computer will just build the code for you, and it'll prepare, a sheet for you to see how much memory you're utilizing, whether your hardware can actually flash all of that code or not, right? So just go through that again. At the last, how many kilobytes used and whatnot, right? And then finally, write the code to the firmware. So by default, the code that ships will definitely get flashed successfully on your flight controller if you ever try to do that. And once you upload the code, it's, again, a simple command. It's a make command as well. You're ready to work with your flight controller, right? And the steps from here on out, if you actually own the hardware, works the same way. We're going to use the simulator, which also just substitutes the second point, where instead of building the code for the target, we're going to build it for the simulator, right? Now, we've seen this before, but just coming back to it, because now we need to start thinking about how we're going to read messages from the Pixhawk firmware, right? So as I said, we have a client and agent setup, right? And this client agent setup, the client is already installed on the firmware. Again, we're not going to touch that. It already exists, and that's already given to us, right? This agent has to be installed on, say, our Raspberry Pi, right? The computer that's running ROS, and the one that the Pixhawk is connected to via USB, right? And again, same story. The documentations are amazing, and you can kind of install it. It's as simple as a single command to install this on an Ubuntu machine at least, right? And this is where the second part comes, right? Where we were exchanging string messages before in the topics. Now we have to exchange messages that the PX4 Autopilot knows, right? This might be a data structure of a bunch of float data that tells the that transmits data about how fast the robot is moving, the velocity, speed, location, so on and so forth, right? So before we can start receiving that data, we need to tell our ROS system that, hey, look, these are the data structures that will be received from certain topics, right? And again, here we don't need to do a lot of hard work because the autopilot firmware provides all of that information. We just need to pull that code and install it on our system, right? So 3 simple steps. First, we clone the repo, right? Then we build the workspace again, right? This time the workspace is building 2 packages, as you can see. It's building our package 1, and it's building a px4 messages, right? And once you've done that, you can already start reading the topics. So ROS2 topic echo is a quick way of getting all the ROS topics on your terminal. Whatever's there on that topic gets printed as text on the terminal, right? And you can see now the system can actually read messages coming through from the Pixhawk. So here I just printed out the battery status of a robot. So Pixhawk actually has a sensor to read your battery voltages and whatnot, and so you can just print that out. But there's a lot more data that comes through Pixhawk. You can get the IMU data, which is your velocity, position, acceleration, compass, right? And then you can get GPS, and you can get logs even, right? Like when your system is erroring out and whatnot, you get logs out of it as well, right? And there's a lot more data that you can use directly in your algorithms to control the robot to do certain behaviors, right? And finally, all that data, since I don't have a robot, you would think where that data is coming from. Well, it's coming from a simulator in my case as well. And a simulator can completely sort of replicate external hardware. In our case, for PX4 Autopilot, there are a few edge cases, but it mostly does well in helping us develop our stuff at Clearbot as well, right? And in our case, we're just going to use a classic rover simulator, right? So once you run the simulator, it behaves as if a Pixhawk is connected to the computer on which the simulator is running. And so we replicate somewhat the same setup without actually having the hardware, right? All right, so we've introduced you a little bit to most of that. As you can see, we've got into the screen, which is somewhat our goal for this. We just need to start making it move, right? We've talked about how to spin up a simulator, how to set up the communication between, well, let me just help you revise, right? How to set up the communication between ROS and Pixhawk, right? And how to install that. And finally, and finally get to the screen where we have a simulator runner. All right, now comes the logic part of it, which is the final module for putting all of this together, right? And we've learned about Pixhawk, we've learned about ROS, we've learned about PX4 Autopilot. We can use some Python code to take the data that the flight controller is giving us, right, and send data back to it to instruct it to do something. And that's where Python comes in. We can use Python to write our ROS nodes to do exactly that, right? So that's what I'm going to cover in the final module. For that, I'll take another 2-minute break. Just give me a minute. All right. OK, so we were talking about topics. Now, these are the 4 interesting topics that we are going to use to make this robot move in a straight line, right? One is the off-board control mode, right? We'll explain a little bit more about off-board control mode later, but this is an essential control mode that allows our Raspberry Pi to control our robot that's running on the Pixhawk, right? And then there are 2 commands that are really, really important to command the vehicle to do something. One is appropriately named vehicle command, and the other one is a vehicle command acknowledgement, right? So the first one tells the robot to do something, the Pixhawk firmware to do something, right? In our case, it would be to arm the robot. That means to get it ready to start accepting commands to move something, to move the motors, right? And an acknowledgement which comes from the controller. So we know that the controller is ready because it sent an acknowledgement that it's taken the command and can start running, right? And the fourth one is something called a vehicle thrust set point. Now, this thrust is simply engines being told to move in a straight direction or being given more power to run in a certain direction, right? So we'll use thrust to basically move the robot in a straight line. And you can control this thrust value to make the robot go faster or slower. We are just going to make it run in full speed, right? So again, what's off-board first? Let's get an understanding of that, right? Since this is running our drone motors and it's controlling directly our actuators and servos and whatnot, we call this PX4 autopilot firmware and the hardware with it on board, right? It's virtually on board. That means it's directly controlling all of the physical stuff on our robot. Now, while this Raspberry Pi is still probably sitting on our robot, right? But because it's not directly controlling any of the stuff, we call it off-board, which means that it's the one that's kind of sitting away from the control systems, but instructing the robot to do things, right? So when we want to control something in an off-board control mode, we say that instead of controlling it from the flight controller directly, we are giving the raw control information to ROS running on a computer off-board, and then we get the instructions from the off-board computer on the PixHawk to execute the commands. And so the first step is to deal with this off-board control mode. Tell the flight controller to go into off-board control mode. There's a computer that needs to control and just instruct the computer to instruct the flight controller to go into that mode. And it's actually quite simple, right? We use a similar concept that we did before, where we create a publisher that goes towards the FMU. The FMU here is just the hardware, the flight controller. And we say that publish a off-board control mode message to the off-board control mode topic, right? And so here our PX4 autopilot is going to be listening to this topic and know that this off-board control computer is there. And we'll make our ROS node send this data about every 100 milliseconds. Now this is required because what happens when the computer gets disconnected? How does the PixHawk know that the flight controller, that the off-board computer is not there anymore, right? So the only way for it to know that is when it has a frequency at which the computer is going to keep telling it that I'm there. And then when it's not able to match that frequency, it's just going to know that this computer is not there anymore. And this message has some really simple parameters in it. These are the different kinds of off-board modes that you can set your PX4 autopilot to be in. And I told you that we are going to be controlling thrust of the motors to control our robot, right? So I'm just going to set the thrust and torque to true and rest all of them to false. Actually, there are ways where you can define the robot to go to a certain position. That's the very first mode. And that's quite interesting. That's something we do at Clearbot, where we build paths out by defining positions of where we want our robot to go. And all of the feedback loop stuff can happen on the PX4 autopilot to go to those certain positions, right? And this message is just sent to the flight controller like a heartbeat, right? So it keeps the off-board control mode running. Then the second one is, the second and the third message types that I told you about is the vehicle command, right? And here as well, we are going to take a vehicle command topic that is expected from the flight controller. And we are going to write a small piece of code to publish that vehicle command data as well. And this is simply to arm the robot. This is more of a safety mechanism where we tell our robot that you can engage the motors now to start running at the thrust command that is given to you, right? And you can see that something as simple as a function which defines the different parameters. So we set some defaults in the function itself. So depending on whatever command comes in, there are some specific defaults, right? And then there is a vehicle command message, the parameter 1 and 2, which define what the actual command is and what do we want that command to do, right? And in our case, you can see the call to vehicle command, to send vehicle command is a vehicle command component arm disarm. So you can see that you don't really need to know a lot of the underlying hardware and how it's implemented. A lot of basic constants are already defined for you. You can just use them, where you can say that you want the vehicle to be armed, which is the 1.0 that you see. And a 0.0 later is just to say, don't force it, just do the arm. So you just always leave it as 0.0, and you don't need to worry about it. Right? So 2 steps. You create a publisher to send a vehicle command, and you publish the ARM command on the topic. Now, a little bit of a note about vehicle command. You'll have to go sort of digging into the documentations to really understand what are the things that vehicle command can do. But there's a lot of things that vehicle command can just do for you, right? So Quicksock firmwares are usually powerful like that. PX4 Autopilot is super powerful. It gives you very fine-grained control to do all of this, right? Since arming and disarming using this topic is quite easy, we just use that to do so here. Now, finally, once the vehicle is armed, we make the vehicle move, right? And here, we just need to send a thrust command to the flight controller, right? So again, a topic that the flight controller, FMU, is expecting as an input is a vehicle's thrust set point, right? And we send it a vehicle's thrust set point message type, which is already defined by the PX4 messages package, right? And this time, we send it every millisecond, right? Where we tell the controller that, hey, every millisecond, make sure you're applying a certain amount of thrust to move the robot forward. And we define a function to move forward, which is if the robot is in an armed state, right, set the thrust, create a message called vehicle thrust set point, and this message.xyz is where you define which direction you want the thrust in. So just defining x to be 1 and the rest to be 0 is just saying move the robot in the x direction straight forward. Now this xyz is not in perspective to global xyz, it's in perspective to the robot's local coordinates, right? So saying that move in x direction forward is like saying from the robot's point of view, move straight, right? And that's what our robot allows us to do. Our robot is just 4 wheels, just like a car. So just when you apply thrust, it moves forward, right? And you just keep publishing that message every millisecond, right? And that's exactly, again, there's some details in it which I should tell you I've hidden is how did we get the vehicle self.arm state? It's from the command acknowledgement that obviously I didn't show you the code, but this code is all on GitHub. You can go to my GitHub, it's all public, and go through it. I'll have a QR code for it later, right? And that's how we get the ARM state, and there are a few things here and there. For example, how does this code get structured? It's in a complete one single node. It doesn't need to be multiple nodes because you can subscribe and publish to in the same nodes itself. Again, all of that on my GitHub, you can go and have a look. But eventually, when I build our package 1, and I run our simulator, so this is running the messaging from by the middleware. And then after building the command, when I run this ROS2 run package 1 control, right, it runs the robot and it moves it forward. Now, I have been told I don't have enough time for this. And there is a lot of code, but as you can see, I've tried to fit it in one screen just to show you how it looks like. It's on my GitHub. I just have a minute, I'm being told, so I'm not going to try and go through this. Very, very basic. Our init function on the top has all of the declarations for our publishers, subscribers, our ARM state. Then you can see the vehicle command acknowledgement, which reads the vehicle command acknowledgement message and sets the ARM state according to that. Then after that, we have an off-board control callback, which is just sending the off-board messages. and then our rest of our business logic to arm the vehicle and move the vehicle forward. All of this fits somewhat in one screen. I know you can hardly read it, but you can go through GitHub and you know that's how the basic structure is. And this is end-to-end the whole code, right? So something as simple as that can help you get started with it. Thank you for listening. You can contact me on GitHub, Instagram, Twitter, whatever. This page is kind of a Linktree website. You'll find everything about me over there. And you can read more about my company, Clearbot, there as well. If you're interested in working with us, hit me up, Twitter, Instagram, GitHub, wherever. I'm totally open for that. And you can read my blog. I've written some posts about this exact talk. Yeah, thank you so much.
Okay, so there we are opening for the question. Okay, from the first one. So how much iOS code at Clearbot is in C++ and how much is in Python?
That's confidential information. How much of it is in C++ and how much it is in Python? I think we go through a phase where we initially write things in Python just to prototype and quickly test if things work, right? And if things work really, really well, we kind of try and port it over to C++ just for performance sake, right? We've noticed that it helps to have the static typing and whatnot, but at least the initial parts of it where we really want to move quickly and we want to build something out to test it, Python is great for that. So how much of it, I honestly don't look at it on a day-to-day basis now anymore, so I could not tell you, but we do both C++ and Python. Yeah.
Okay, so the next question is from Neil. This one.
What point can you give us some idea on bandwidth, payload frequency? I don't think any of this is a limitation of Python or C++. I think ROS natively supports both Python and C++, and you'll have to be doing some really, really heavy work to kind of notice the bottleneck where Python becomes a problem because of payload or frequency of data. I think it's more that when you start deploying code on hardware on the edge where you're not going to have control over it, you want to make sure that it works 100% of the time, and there's some very strong rules that don't let you make the mistakes that you would want to avoid in the first place, right? And so, and of course, there's a little bit of a performance advantage that you will see with C++ than Python, but you would have to be doing a lot of work on these to see payload or frequency bottlenecks. I think when do you switch to C++ when you feel like Python isn't fast enough for you, which you'll kind of notice it in robots because they start misbehaving very quickly, right? So when you see that happening to your robot, you can think about whether you should consider a language that will help you process things faster, right? Yeah.
Okay, so we have another question.
Yeah, is the subscriber publisher architecture a standard for robotics? I don't know if I should be commenting on what the standards of it are, but I can tell you this, that it's super easy to get started in this way, right? Because you're working with hardware where you have multiple sensors, lots of data from lots of different sources, and you want to work on each one of these data points as they come in, and let's say you're doing some kind of feedback control, you want to make sure you're reading each of these messages and processing them as you go, right? So pub/sub pattern kind of helps you to decouple a lot of the code that you write. So any one single piece of code that does a certain thing on a data does not need to depend on the rest of the code that you've written. You can just kind of isolate that one processing task and just have a message come in, process that message, and publish it somewhere else, right? And so it makes things really, really easy in robotics because none of it is like very reliable. Like none of it is timed. Like all of this is happening at its own. Like all the processes are happening at their own time. So a pub sub architecture really makes sense because you can work on data as they come in, publish data as it's done, things like that. I hope that answers the question.
OK, so 现场有任何问题吗？没有任何问题可以举手。Okay, so if there is no question, we would like to thank Yuju for the wonderful talk. Thank you.